Welcome everybody to Uniper Energy Storage's presentation on hydrogen storage. My name is Doug Waters, I'm the Managing Director of Uniper Energy Storage, and I'm going to talk to you today about our new hydrogen storage project in Krumholm and how it fits with the wider energy transition. So a bit of background on Uniper Energy Storage. We are the largest gas storage operator in Germany, and together with our assets in Austria and the UK, we have about 83 terawatt hours of natural gas storage. Of course, natural gas is part of the energy transition, but so is hydrogen in the future. So we're working at the moment on how we can store hydrogen to get ready for the hydrogen revolution. A bit of background on hydrogen storage and how one can use hydrogen as an energy vector to store electricity. So if you think about electricity coming from renewable sources, that is intermittent. We can use electrolysis to make the excess electricity into green hydrogen, and then we can store that underground and use it when there's not enough renewable electricity to make power or as a feedstock for a number of industrial processes. So what does that look like? So if we have on the left-hand side hydrogen production, then we have hydrogen storage in the middle, and then we have hydrogen consumption and use cases on the right-hand side. And my colleagues in the Uniper hydrogen team are concerned with the hydrogen production and import and the hydrogen use cases, and we in Uniper Energy Storage are concerned with how we can store hydrogen in the future. And part of our objective is to get that use case ready for when the hydrogen revolution comes. If we look at the different types of underground gas storage, we have two options. So porous rock storage, which is predominantly in the southern Europe and the south of Germany, and Kevan storage, which is across the north of Germany, the UK, and then into Denmark. And we're starting with Kevan storage for a number of reasons. It's easier to size that correctly for a small test project. It's also closer to where the first hydrogen projects are likely to be in Germany. So if we look at how we can see the future, we can see that infrastructure will develop as individual projects to start with. Then those projects, those clusters will join together, and ultimately there'll be a hydrogen network in maybe 10 or 15 years' time. And we can see that planned hydrogen network on the middle slide there. And then also on here, you can see where the salt deposits are in Germany, which seems to be very consistent with where the first hydrogen projects will be. One of the other key considerations we have is the energy density of hydrogen is a lot lower than the energy density of natural gas. And what this slide shows you is that if we replace all of our cavern storage for natural gas in Germany with hydrogen storage in the same caverns, we see a huge reduction down to 20% of the energy stored. So that's a challenge the industry needs to think about as the hydrogen use cases become more certain. One of the other aspects we've been exploring is the blending of hydrogen with methane. And I guess blending hydrogen and methane is relatively straightforward in the transmission system, but when we get into storage with the high operating pressures, we start to see challenges around metallurgy, bio effects in the storage sites, and I guess other concerns of how we'll deal with the integrity and so on. So our first studies in this area have seen that a small blending, sort of 2%, is relatively straightforward, but when we get to 10%, we start to see significant technical challenges in that area, which could mean replacement of all the infrastructure on site, for example. And then how do we see the early market till 2030? Well, I guess the hydrogen use cases are still becoming clear. How will hydrogen be used? In what sectors first? The locations are becoming more certain. And I guess for us in Uniper Energy Storage, it's about having a project where we can prove the concept of hydrogen storage before the real commercial projects come. And that's where we positioned our Krumholm project. It's a project where we can learn, the industry can learn, and then as hydrogen becomes more commercially available, we can take that learning into hydrogen projects. And with that, I'll hand over to Sebastian. Sebastian's the project manager for our project at Krumholm, which is our first test project for hydrogen storage at scale. And so, Sebastian, over to you.
Thank you, Doug. And welcome to the Uniper booth also from our side. So we are going to present the hydrogen pilot Kevan project in Krummhörn. And so I'm the project manager, and my colleague Martin Streher, he is responsible for the surface facilities and hydrogen technology. Having a look to the worldwide situation, so far there are only a few Kevans which are equipped for hydrogen operation and are already in operation so far. So basically there are three Kevans in operation in the USA. It's the Clements Dome, Moss Bluff and Spindletop. They are all in the vicinity of Texas. And there are three Kevans in the UK, in the northwestern part, close to Teesside. Whereas the US Kevans are very similar to our typical gas storage Kevans. So in respect to size and to pressure regime, the UK Kevans are significantly smaller, and they are operated at a lower pressure. So in fact they are operated at a brine pendulum scenario. So brine is injected for withdrawing of hydrogen and vice versa. So these few storages, they are already in operation since the 1970s, 1980s, and still there's little experience available in the technology. And also the relevant standards for Kevan completion and the Kevan construction is not really available yet. On the other hand, as already heard, there's an increasing demand in hydrogen storage, and it's predicted to start in the next years. And therefore, Uniper Energy Storage has decided to develop the hydrogen technology in the near future. So coming to our project, in that line, Uniper Energy Storage intends to build a pilot Kevan and storage plant at its site Krummhörn until 2024, and to carry out a test phase to investigate the hydrogen storage in salt Kevans. The motivation for Uniper Energy Storage is by several aspects. One is to test the hydrogen storage operation and technology in a real environment at a demonstration plant. Second, we are going to understand the permitting process and the requirements. We already see in the first phase that it's already for the authority process also a new starting technology, and they need to learn the processes as well. We are going to investigate the materials, the subsurface and surface installations, and the functionality of individual components. All in all, we are going to develop a storage solution for green hydrogen on a commercial scale. So the Krummhörn hydrogen pilot Kevan, it's constructed in Krummhörn, which is in the northwestern part of Germany, close to Emden, and it's at the gas storage site of Uniper. On the right-hand side, you see the time schedule of the project. So we have already started with the permitting phase, and we are now in the basic design phase, which are going to continue until the Q1 of next year. The procurement is planned to start in September next year, and we are going to start with the constructions in the field in Q1 of 2023. And finally, we plan to fill the Kevan for the first time with hydrogen and conduct the test phase in January 2024. Some project key data. The Kevan will be leached to a volume of 1,000 cubic meters roughly, which is comparably small if you look to our typical gas storage caverns, which are about the factor 500 to 700 larger than this Kevan. The pressure regime is at 70 to 270 bars. H2 capacity is 200,000 norm cubic meter, which equals to a energy of 700 megawatt hours. H2 working gas capacity 150,000 norm cubic meters or 520 megawatt hours, and we are going to achieve maximum flow rates of the hydrogen up to 1,600 norm cubic meters per hour. So in this slide, the technical phases are displayed for the subsurface part of the project. We are starting with the existing borewell K6. So on the site there are 3 gas storage caverns which are currently out of operation, and we use one existing borewell which is already drilled and partly cemented, and we will install the cavern at the bottom of this well. Before starting the solution mining process, there will be a tightness test with the medium of nitrogen, which is typical for the construction phase of a gas storage cavern. Having conducted this MIT, we are going to leach the cavern. So we are going to leach the cavern at the bottom of the borewell, which gives us the potential to later enlarge the cavern and to scale it up to a potential commercial case. And after the cavern has been leached, the leaching strings will be deinstalled from the cavern, and there will be a second mechanical integrity test, this time with hydrogen. So the cavern will be ultimately tested for its readiness against hydrogen. And then we are going to install the underground completion. The underground completion is quite similar to the completion of a gas storage cavern, but there are different aspects to functionalities and to the material. Finally, after the completion is installed, we are going to fill the cavern the first time with hydrogen. Therefore, we are going to install a brine removal string, and we will inject the hydrogen in the annulus between hydrogen production string and brine removal string. And by this injection, we are going to produce the brine out of the well until the cavern is completely filled with hydrogen. At this point in time, we need to deinstall the brine removal string. That will be done at high pressure and under a hydrogen atmosphere. Therefore, we need a so-called snubbing unit. And under this pressure, the brine removal string will be deinstalled from the cavern. Then the cavern is finally completed, and it's prepared for the testing phase. And during the testing phase, we are going to invest different aspects. We have already defined a suitable investigation program, and several aspects are described here. So the one part are the materials tests. So we are going to test the steel, some plastics, elastomers, and also special subsurface components like pucker and subsurface safety valve, which are going to be investigated in the lab before the project, and during the project, during the testing phase, we will investigate it in situ under real storage conditions. We also are going to apply the typical exploration and production services, and need to see their readiness for a hydrogen atmosphere. So this is due for measurements and for surveys, for wireline jobs and similar works. A very important aspect is the quality of the hydrogen. So we are going to investigate and determine the hydrogen quality before storing it into the cavern. And after the storage process, we will analyze it again and see if there's any effect by the contact with the salt walls or in contact with the fluid brine sump. And this is very important for the design of our treatment plants on surface to bring the hydrogen in the right condition to deliver it to the clients. Other aspects are the thermodynamics and the process parameters. We are going to measure the pressures, injection rates, and the temperatures during the whole storage process, and we are going to learn from it and will calibrate our operational software, which is designed for gas storage, for natural gas storage, and we will calibrate and make it fit for purpose for the hydrogen storage phase. Another aspect is the rock mechanics. So the Kevan will be designed for the hydrogen storage under a specific scenario, and we are going to test different pressure build-up rates and different flow rates, and we control the contour of the Kevan and the integrity of the Kevan by frequent sonar surveys to see if the Kevan is still in an integer situation. So now we are going to describe also the surface facilities which we are going to install for the hydrogen pilot Kevan, and therefore I'm going to hand over to my colleague Martin Streher.
Okay, hello everybody, welcome. I'm Martin, working as a project manager with Uniper Energy Storage. And yeah, in this project I'm the sub-project manager for the surface facilities and hydrogen technologies. So yeah, Sebastian told us a lot about the Kevan itself and the brine process. I would also like to present to you now the different ways that we are injecting and withdrawing the hydrogen into and out of the Kevan. Okay. So yeah, I will start with the injection process itself. So for the injection of the hydrogen, we have mainly two ways. One way will be using liquid hydrogen, which we are going to supply by truck, and in an evaporation process, we will evaporate the hydrogen into gas and pump it into the Kevan itself. So you can see this this way here into the Kevan. The other way to inject the hydrogen, we will use an electrolyzer where we are in a partnership, and where the hydrogen is going to be generated by a pressure of 30 bars. So we will need to also install a compressor and a puffer tank and inject it also through this field piping into the Kevan. For the withdrawal process, we will use the same field piping as we injected the hydrogen, and we'll go through a hydrogen treatment unit where the hydrogen is it's reduced. The pressure is reduced from 270 bars to around 70 bars, and we will also cool down the hydrogen and also dry it. So there are different technologies for drying. In this project we will test two different technologies, the adsorption and absorption process. Also here we will have a partnership for the adsorption process. After the treatment we will have 4 different use cases for the hydrogen. So the one use case will be the injection of the hydrogen into the transmission grid, where we will, together with OGE from at the site, injected the hydrogen into the transmission grid. And the other one will be the re-liquefaction of the hydrogen and the transport by a trailer truck. For the other 2 use cases, depending a little bit on how well the treatment will function, if we can achieve a hydrogen quality of 5.0, then we will also use this hydrogen for the fuel cell power generation and or the hydrogen fueling station at the site. All right. So one last thing, also very important. This field pipe, it's already an existing field pipe, and it was built 40 years ago for the use of natural gas. And in this project, we will also try to qualify this field pipe for hydrogen, so that we can use it at least in test phase, which will be for around 2 years, more or less. All right, that's it from the surface facility side. So thank you very much for listening, and if you have any questions, thank you very much.